So I'm an applied statistician primarily, and a lot of my applications are in statistical ecology and epidemiology, and we'll see some of them today. My initial work was a lot to do with model uncertainty, model selection, and model averaging. But in a lot of this work that I've been going through in my career, I often have to deal with things like missing data. And I keep coming back, with all different problems I'm looking at, I keep coming back to many of these models can be specified as a simple hidden process model. And by that, I'm including things like hidden Markov models, state space models, so that general form. And I keep coming back to this all the time, and it's made my life an awful lot simpler. Once you can recognize that a model I was struggling with is fitted into a nice framework, we have lots of standard tools for dealing with it. So this talk is really sort of my recognition of this happening time and time again to me. So mainly, I've already sort of said that, I'm going to be looking at how hidden process models are so useful. And they're nice and generic, so I'm trying to present it in a nice generic way. And although the applications I'm looking at are largely in the statistical ecology, and one example in epidemiology, many, many different areas fit into this hidden Markov or hidden process model structures. So what do I mean by some form of hidden process model? Well, we typically observe data. I'm always interested in trying to understand something about a system, primarily linked to animals in statistical ecology. And in order to gain some understanding of the system, we collect data. And then from that data, we want to learn about the underlying system. Now, the problem is when we collect data, we often do so in such a way that we typically can't observe the whole population. We might take some sample from that population. So we have to take into account the sampling variability. So we can think of it this way, that we have some true underlying process that we're really interested in, and from that we sample from it. So we have a true underlying process, and then we have an observation process that sits on top of that underlying system. But we don't observe that true underlying system. So we can think of that in some ways as missing data, and we'll come back to that later. So this is the whole point. We have some underlying process, and we have a second process on top of that, which describes how we observe it. So this is our notation that I'm going to use. We've got our observed data, and for simplicity, I'm thinking of that it's a sort of time series data. Could be univariate, could be multivariate. It doesn't have to be time series, but just for ease of notation. We have our observed data, what we actually see at time points 1 up to capital T. But what we typically actually have, they're just the observations or sampling from the actual true state. So we have the true underlying states y1 up to yt, and we don't typically observe those y's, we observe the x's. And then we define a statistical model to describe what's going on in the system. So we have a system process that is talking about how the system evolves over time in our case. So it's just specified on what's happening at the true population level. That's our sort of the hidden process underneath, and then on top of that we have the observation process. Given what the true state is at a given time, what do we observe? So the process of observing things. And we're going to split these up completely separate and think about them as two distinct processes. And then we combine them together to get our whole statistical model. So for anyone who has ever been to a hidden Markov model talk, this is the compulsory diagram that we have to have. And it just describes what I've said. So I'm getting a bit short, so I'm going to use this. So we've got these are our true process over time, how it evolves. And we're assuming in this case it's a first order hidden Markov model. So the state you're in at time t only depends on the state that you're in at time t minus 1, and nothing else. So your current state only depends where you're going to next. And your observation process, so given the current state, what you observe is just a function of what the current true state is. This is the simplest first order hidden Markov model. This can be relaxed, we can have feedback loops, we can have higher order Markov processes on the system, but we're largely going to stick with this one for the purposes of today. So that's the nice obligatory diagram that explains what we're doing, and then we have the associated mathematics, or how we write this down mathematically, which is what we have here, the two processes again. We split them up. We have the system process. How does the system evolve over time? And it's just some stochastic process. So given that you're at state yt minus 1, what are you at time t? It's just a function of where you were at time t minus 1 and some model parameters that we're interested in. So that's just going from one time step to the next at the true population level. So then that's the first process. And then the second process, which is really of less interest, but we have to take into account, is the observation process. And again, we assume that what we observe is just a function of what the true state is and some other model parameters. I mean, I've just put theta to be the set of all model parameters. Typically, these will be mutually exclusive. So that's nice and straightforward. We can write down the mathematical model. So whenever we start writing down the mathematical model or statistical model, we then typically want to estimate the associated parameters. So we're typically wanting to estimate the model parameters. That tells us how the system is evolving over time, tells us about the system. We might also be interested in the true states. We'll come back to that later. But particularly think we're just interested in estimating theta. In order to do that, we often will use the likelihood function. So you need to specify the likelihood function, and then we can either estimate the parameters in the classical framework, typically the maximum likelihood estimates, or derive their posterior distribution in the Bayesian framework. Both rely on the form of the likelihood. Now, if we have discrete states, so if the true underlying states, the y's, are discrete, that simplifies everything. And that's what I would typically call a hidden Markov model when we've got discrete true states. Then we can write down the likelihood in a nice simplified way. And what we have is this. We have, gamma is the transition probability matrix. I've dropped the notation on theta for simplicity here. So this is just the probability you go to state yt at time t, given that you're at state yt minus 1 the time before. So it's just the probability between each possible state at time t. So it's your probability transition matrix, probability of movement between each true state. And then the Q is simply the observation process, and it's a diagonal matrix. So that means it's typically very straightforward to calculate this likelihood. And the pi 0 is just the probability of being in each state at the initial, at time 0. So the likelihood, if we've got discrete states, is nice and explicit. However, it gets a little bit more complicated if the y's, the true states, are continuous, because we will lose this nice system here, and rather than being able to write it in nice closed form, we end up getting an integral. We have to integrate out over all the true possible states that we have. And unfortunately, this integral is analytically intractable in most cases. So that gets into the problem. We haven't got an explicit form for the likelihood. If it's discrete states, we're fine. We can just do what we like. We've got the explicit likelihood. If it's continuous true states, we've got an analytically intractable likelihood. So what do we do in that case? Well, in the special case that we have Gaussian linear observation and system processes, we can use the Kalman filter. However, that's not often the case, so we can't use that approach, so that we still have this integral we have to deal with. So my background was using Bayesian data augmentation. So what we do here is we treat the true underlying states to be parameters. We form the joint posterior distribution over the model parameters and the unknown states, given the data. Then we can write down the expression for this posterior distribution up to proportionality at least. And then we can do standard techniques for sampling from the joint posterior distribution and then marginalizing in order to just get a sample from posterior distribution for the parameters theta. And we can do that using standard MCMC. So that should be nice and straightforward, but we'll see that's not always the case, because this happens. So this is an example of a real example where we have some count data of animals, And we did a standard MCMC. And the problem is, if you look, I mean, this plot was bad enough. Look, this is a lag 3000 of the ACF plot. I mean, it's pretty dire. You can still run this, but you have to run it for a very long time. It's exceptionally inefficient. And the reason is because of all high correlations between all the parameters. And this was doing to be fair, this was doing a single update MCMC. You can do some clever stuff, and I'm currently working on trying to do some clever stuff. This plot doesn't look so bad until you realise, again, I'm still on the lag scale of 3000 by the end. So, what happens if we don't want to be Bayesian? Then, well, actually, we can do some other clever stuff. So this is largely work done by, some work I've done linked to this based on work that Roland Langrock had done, who's now in Bielefeld. We worked at St Andrews together for some time. And the idea is we have an integral, but we can actually approximate that doing just a discretization. So the simplest thing you do when you do an integral, if you think trapezium rule in one dimension, we're just doing that here. So what we have is this is our range of possible values that the true state can take. We just discretize it. So we just finely discretize it. And then we consider the midpoint of each bin. And then we want to calculate the probability of going from, say, this state to the future states. We just work out the probability we fall into the continuous range. And we can do that because this is some function is normally straightforward. It's a standard, nice, simple PDF. You could just do it midpoint to midpoint, but this is going to be obviously more accurate. So this is an approximation, but you can make these bins fairly fine, and it works fairly well in practice. So that seems quite nice. The problem with this approach, though, is that we get the curse of dimensionality. So it works in one dimension. Once you go 2, 3, you can't, because the number of bins you have become infeasible to be able to do the summation. So, as I said, well, I realised missing data falls into this framework. So a lot of my work now can be regarded as simply a special case of these general problems. And rather than having these observations, x1 up to xt, observed, it may be that we don't know some of them. So I've expressed it as an NA. So we don't observe a particular value. So then what happens there? Well, exactly into this framework, but the observation process changes. The system process hasn't changed at all. That's continuing on along as normal. It's just what we're observing is changing. So again, the system process stays exactly the same, and we only have to modify the observation process with missing data or missing observations. And if we just have the probability that if we don't have an unobserved value, the probability we have an unobserved value, if it's just a constant, then it's missing at random. We can just estimate. Q is the probability of observing the value. But we can then have not missing at random, where actually the probability that you have an unobserved value is dependent on what the true state is. So it's a nice simple representation of missing at random, missing not at random. And similarly then for observed data, we typically can only observe the true value, and we observe the true value with the same sort of probability idea. So missing data is just a special case of hidden process model, where you may have some values observed and some unobserved. So let's give some applications. When I realised actually what I was doing is simply a hidden process model. So this is work I did a few years back with Anthony Overstall, who's recently moved to Southampton. And the idea is we have contingency table data corresponding to observations of injecting drug users in Scotland. So we have 3 sources, A, B, and C. A 0 meant that the individual was not observed by that source, a 1 that it was observed. So for example, N011, number of individuals observed by sources B and C, but not A. So that's all well. And typically what you're interested in is estimating the number that you don't see. And you can, standard methods now for doing this. Actually, this was one of my very first project I did as a PhD student, was involving this. Want to estimate the number that we don't see? Well, we just fit a fairly standard generalized linear model to the observed data, which then allows us to estimate the missing cell. And that's all fairly standard, and we can do model averaging and model uncertainty and so on. But a particular problem arose in this data set where this number here is a bit more complicated than I have. I've simplified to the problem. The number of individuals only seen by C, this isn't the number of individuals, this is an upper bound. Because this was injecting drug users, and some, well, for this particular cell, it identified not only current injecting drug users, but past injected drug users as well. So it was a mixture of current and past users, so this is actually an upper bound. And then I realized this is just, can be formulated into this hidden process structure. So what we have is we have all the observed values, and then for this particular value, then we just have a different observation process. So again, system process stays exactly the same, it's just what we observe given what the true value is. And it just changes for this particular cell. I don't really want to go into the details, it's just the fact that we can simply write it down, and we just add another parameter to estimate. And we did that, and it had quite a big impact. So this is for, we applied this method to 4 years of data of injecting drug users in Scotland. Don't worry too much about anything, apart from what you need to look at is the dashed line and the black solid line. And if you ignored this censoring of the cell, so you presume that the number you saw in that cell was the true number of current injectors, you get the dashed line, estimate total population size. Whereas if you take into account the censoring that we had in that cell, and said actually the observation process is different for that cell, you get the black solid line. So these are posterior modelled averaged estimates of the total population size. And you can see if you ignore the censoring, the estimates you get are significantly larger, which worried them in the first instance, which actually led us then to go back and look at the data in more detail. But it was quite nice that we fitted into this hidden process structure. So that's the first simple example.
How do you know what the correct answer is?
What we actually did as well was remove that we had 4 sources. One of them was a problem. We removed one of the sources, and that's the grey line. And we get very similar estimates. We've done a bigger simulation study as well on this. I can give you the reference if you're interested later. So that was simple example 1. Simple example 2. Now this is a really simple example that you're going to ask me in a minute why we need to be worrying about putting it into a hidden process model. And hopefully it'll become clear. So this is a very simple model, simple sort of data. It's called capture-recapture data. And what happens is my biologist friends, because I'm a bit of a coward, I don't go out in the cold and the wet, they go out and collect data on some animals, for example some sheep. They go out at a series of discrete capture events. At the first capture event, they round up all the animals they see, they uniquely mark them and let them go again. And then they go out at the second capture occasion, do the same thing. But because they have uniquely marked the individuals they've previously seen, it means if we see an animal again, we know we've already seen it and we can uniquely identify that animal. All new animals are marked and released and so on. So what you get is a capture history of each animal over the study. So a 1 means an animal was seen, a 0 it wasn't. So we've got this first animal was seen at times 1, 4, 5, 6, 7, and not at times 2 and 3, and so on. And then typically you can write down an explicit likelihood function for this. It's a function of 2 sets of parameters, capture probabilities, think again observation process, and survival probabilities, so that would be system process. And it's just to show you that you can write it down. You just have the probability that they survive and the probability that they're captured or not. For each individual capture history, we calculate the corresponding probability of the capture history. Very straightforward. It's a little bit more complicated in this example because we don't see the animal after time 5, so we don't know whether it's died or that it's survived and we just haven't seen it. And you get this chi term, you can write it recursively, but you can write it down. That's the main thing. So we don't need to make our lives more difficult, but we're going to express this as a hidden process model. So the nice thing is with the likelihood, we've got discrete states here for an animal. So if you consider one animal, they're either alive or they're dead. And if they're alive, they're available to be captured. If they're dead, they are not. You can extend it where you can see dead animals, and it's fairly straightforward. So we think of our system process. We have an animal. Once it's in the study, it must be alive to start with because you've seen it. It can either stay alive or it can die. And all we have to do in the system process is to define the transition probability matrix, the probability of it moving between those two states, dead and alive. And once an animal is dead, that's an absorbing state, it stays dead. So it's fairly straightforward, two-dimensional transition probability matrix. We have states of, state 1 is alive, state 2 is dead. They go from alive to alive, probability phi. Alive to dead, 1 minus phi. And if they're dead, they stay dead. So that's the system process. Then we have the observation process. It's a diagonal matrix, and it depends on what the true underlying state is. So the first element in the diagonal is if they're alive, and the second one is if they're dead. And we consider the two outcomes, either we see them or we don't. So if we don't see the animal, well, we don't see the animal with probability 1 minus p if it's alive. We don't see the animal with probability 1 if it's dead, in this case. But basically the main thing is you can write it down in those just two matrices, the transition probability matrix and the observation process matrix, and then they just go straight into that likelihood expression that we had earlier. I don't have to do any more work. So previously I had to calculate this sort of chi-term probability, we don't see it again. That is automatically done in this hidden process model framework. No worries whatsoever. So we didn't need to do it here, but the idea is that these models are really simple. They get a lot more complicated. And it's these extensions that if you put it into the hidden process model framework, these extensions become much simpler. So multi-state models where you have animals can be in different types of states. Breeding, not breeding. So when they're discrete states. If they're when you have states, then there might be some uncertainty. If you see an animal, it's probably breeding, you're not sure. You can have transient animals that basically animals that shouldn't be there, or sometimes called ghost animals. So if you're at a site, they might be migrating birds and they're only there for one time period, so you can't see them again, so they're not really part of the system you're interested in. I spent a lot of my life on individual time-varying continuous covariates, and this is where a lot of missing data arises. If you don't see an animal, you don't know the corresponding individual time-varying covariates, such as weight, and how do you deal with that? So there's lots and lots of things, and each time you have a different model, you have to rederive that likelihood function. If you're doing this traditional way. If you're doing it in the hidden process model way, you just have to either change the observation process matrix or the transition probability matrix. Makes my life a lot easier. So, for example, I'm not really going to go through in detail, just to give an idea. If you have multi-state data, so think of breeding, not breeding, or dead. So in this case, we've only got two possible states. The matrix is nice, straightforward, it adds on. We now have a probability of moving between each of the states given that you survive. But the details are not important, the fact that you can write this down really, really simply. And then we extended that a couple of years ago. And again, it shows the attraction of putting into something like this standard hidden process model framework. If you think of states of hungry and not hungry for an animal, because their behaviour might depend on whether they're hungry or not, if they're hungry, they may take riskier action to get food. So if I'm a snake, whether I'm hungry or not today will not only be dependent on whether I was hungry yesterday or not. It's going to be dependent on when I last ate. So this first order Markov structure collapses. It doesn't make sense. Because in a first order Markov model, probability I'm hungry today or not is simply a function of whether I was hungry or not yesterday. And it really is when I was last ate. If I ate 3 days ago, then I'm probably still not hungry. It might not be till over a week that I start to get hungry again. So the current model I've done, cut doesn't fit in. However, you can reparameterize the system process and change it into these two different terms. You have the dwell time distribution, basically, or distribution for the dwell time, which is the distribution of how long you stay in a state. And then you have the conditional distribution of moving to each of the other states given that you leave the current state. So this breaks up the probability transition matrix basically into two parts, the diagonal and the non-diagonal. And then we can put on nice, more generic models. So for the first order hidden Markov model, the dwell time distribution is necessarily geometric. But we can relax that assumption and specify anything we like. And we did that. And the nice thing is, when we realized we could do this, we already, because of the hidden Markov model structure we've specified for the capture-recapture, we could just borrow from their literature. They've got lots of machinery in the HMM world, and we could just borrow those and port them straight into our problem. And basically what we do is that in order to write down the likelihood, because it breaks the nice expression that we had before, we can actually write down the semi-Markov model as an approximate first-order Markov model. And the idea behind that is basically if you have a state, you just split that state up into substates, which depends. So it'd be being in given state R for one time period, being in state R for 2 time periods, and so on. So you include how long you've been in that state as part of the state definition. And then you're back into first-order Markov model territory, because either if you stay in the state, you've been in that state for one longer time period, or you move to another state and you've just joined that other new state. And we did this for house finches, and just to show that once you've got this nice way you can write down the likelihood in this way, then you can do standard model selection stuff, and you can use all the standard machinery. You didn't have to didn't have to reinvent anything. So this was the bane of my life for many years. This other example is where, rather than having these discrete covariate values for individuals, we have basically their weight, some continuous time varying covariate, and then we've got the intractable likelihood expression again, and we can't do the integration. And again, once we realize, so I used to do this in Bayesian data augmentation for many years, but once we realized that the formulation of capture-recapture into the HMM, we could again borrow the HMM machinery and do the approximate discretization I mentioned earlier. So this is what we could do here, that we discretized, we only had one dimension here, so it was one covariate that was continuous, so we could just discretize that, and we had a one-dimensional integration that we had to do, and we did that doing the approximation I mentioned earlier. So that was all nice, and again, I keep coming back. Every time I'm looking at deriving some new statistical models, they always seem to be leading me back to these hidden process models. And when it does, I'm really happy, because then we can use all the tools that we have available to us. I don't have to invent new things. However, what we do have to do, though, is think about some of the model fitting tools. So as you saw my terrible ACF plot earlier, we can fit them into these nice frameworks, but we have to then think about, do we have problems? How can we improve the model fitting algorithm, because we have a likelihood expression now. So that's some of the things that I'm looking at jointly through summer internship that we had, some project that we had with some people at UCL. Also, something that I'm also interested in getting in is what happens when we got large N, so the number of capture histories in my case that we have is very large, so that the likelihood becomes too cumbersome to be calculating again. So that's something else I'm currently looking at, again, with some colleagues in the Institute. And then further, lots of more interesting things are happening, particularly in the types of models I'm interested in, that we get in new data. So I think this is continuing, but we are trying to port the new data into this nice hidden process framework to make all these nice efficient savings that we can have. Thank you very much.